Okay, so this is from the alcohols, ethers, and epoxide chapter there, and one of the things I want to really kind of point out for at least with the zinc chloride, which is just kind of one of those recommended cheat sheets, we're going from a primary alcohol and we're converting it to a primary, hopefully you can see that, alkyl chloride. So a lot of the primaries is what we're working with, so we know that it's going to be this reaction here with alcohol. This is going to be a SN2 reaction. So let's get into the the reaction mechanism here. So the mechanism. Okay, so we have ourselves a primary alcohol. Here's the lone pairs on that alcohol. And we have zinc chloride. And remember that this is a Lewis acid. Okay, red. I don't know why I always want my electron pushing arrows to be red. So the lone pair on the alcohol is going to be attracted to the zinc. And then what we get is part of our alcohol there, an O, an H. It's now attached to ZnCl2. And remembering our formal charges, we know that this is positive. Up here we had no charges, so it has to be overall still neutral. Positive, negative formal charges on each of those molecules. And if you've learned anything, you'll know that this positively charged oxonium anion makes a really good, not anion, yeah, it's a cation, I'm sorry. Positively charged oxonium ion makes a really good leaving group. So we have a Cl minus here floating in the solution because there's a chlorine there. We'll get to that point later. And if I could draw it here, this negatively charged here works via the SN2 reaction mechanism here, thus creating ourselves a happy primary alkyl chloride. That shouldn't be too conceptually weird for you. But what I find to be kind of weird is the other thing that happens. We have, right in our situation here, is I'm just going to draw it like this, an OH molecule attached to zinc, and chlorine there, chlorine there. Those are chlorines. I don't know how well you can see that. So oxygen is back to its normal self. It's fine. But nothing has really changed for the zinc. It still has a negative charge. So the way that it's going to do this, the way it's going to, I guess nature is going to reach an equilibrium, is this chlorine here is going to pop off. Like it formally does. And this chlorine here is the exact same thing as the chlorine that did the SN2 nucleophile attack. I think in the UC Irving guy that I showed you, he was talking about this and he's like, well, this is one of those situations where it's like, which came first, the chicken or the egg type of a thing. But go ahead and switch to green again. So that pops off. We end up being left with a HO, ZnCl. Nobody cares about that. A chlorine to act as a nucleophile. What's really important is that, and hopefully the most obvious and the most simplistic thing to understand, is that we have made ourselves an alkyl chloride. All these other things are kind of just not stuff that we're really that interested in terms of the reaction. Cool. So again, primary alcohol, primary alkyl chloride through an SN2 mechanism. Moving on, let's talk about another two reactions, and I don't know if we'll be able to fit all these all on the same pages here, but nonetheless they are alcohol reactions and they are both used for certain different purposes, but we're all reacting with alcohol. So the Pockle 3 is what they call it, and I'm going to call it Sockle 2. I'm going to start that trend. I guess the overall mechanism of it though is a E2 dehydration reaction. Okay, so we're getting rid of, or pulling water away from the system. Why do we do this though? So let's talk about why we would want to use Pockle 3. Because this is a way that we can avoid, especially when you start working with other molecules, we can avoid carbocation shifts. That's really problematic later on. So why? To avoid carbocation shifts. So it's E2 dehydration reaction that we're using with Pockle 3. Okay, so let's just go ahead and draw the mechanism. And again, I'll just use a cyclohexane alcohol group attached to it, just because I don't know why I'm doing that. Anyways, so that's your alcohol. Lone pairs there, lone pairs there. I also forgot to, I guess I should have mentioned it also. I'll do it in blue. That both of these, the polycyclic 3, and then they're both involved in pyridine. Plus, and I'll show you why that's important later. Pyridine. Plus pyridine. It's getting kind of messy, but we know what we're doing. So, POCl3, remember phosphorus is one of those exceptions to the octet rule. So there's a there. 1, 2, 3. All these chlorine groups are there. And switching to red, we have our electron pushing arrows here. Attached to there, that goes there, and chlorine is going to be removed as a byproduct. But we're not really, I'm just going to draw it out here. We have a Cl minus, and we'll get there later, but we're going to keep going in this direction here with drawing our steps. So, obviously, we have, there's our, it's kind of hard to draw on this pen, but just imagine that as a cyclo. Oh, man. Oxygen there. Hydrogen there. P. I'm just going to do it POCl2. Kind of running out of room here. But if you've learned anything, or if you've noticed from when we were talking about the last one, this positively charged oxonium anion, there's the negative charge, in case you're wondering where it came from. But the oxonium ion is a really good leaving group. And this is something that's a lot of frustrating to a lot of people. They think, well, hey, this is a really good leaving group. Why doesn't it just pluck itself off already? This is secondary. It's much more stable than other reactions that we've seen. But, you know, even if it were tertiary, why doesn't it just plop right off? And the thing is that proton transfer reactions are way faster than carbocation formation reactions or S substitution reactions. Those are always going to be faster than the others. The thing that's really frustrating about this entire chapter is all these reactions that you're learning about and all the reactions that you're going to learn about in chapter 10 are totally dependent upon the concentrations. So we're just going to make the assumption that we have a lot of pyridine, and I'm not going to really draw it. Well, okay, I'll just go ahead and draw it. Pyridine, it's a nitrogenous base. There. Okay, so even though, and you'll see what I'm talking about later. I'll just go ahead and draw the 3 electron arrows here. So pyridine is going to come in. It's going to steal that proton. I'm going to snag him away from there. And white. That's our next step here. What we have is this O P O Cl2. I'll go ahead and just draw the lone pairs. This was really frustrating for me as well whenever I first started, I guess, taking this course, is the fact that this thing right here is your leaving group. This is the leaving group. This is much more stable than that. So why would we, you know, especially when we're working with acid catalyzed reactions in water, a lot of it was creating a positive charge on the oxygen as a leaving group. This over here, this positively charged oxygen, would make a good leaving group. But because there's pyridine in it, we have so much pyridine in it, this is going to snag that off much faster. And so let's just go ahead and draw in a hydrogen here. There's a hydrogen here. And we have a lot of pyridine in our solution. It's a high concentration of pyridine. I'm just going to draw it like this with the N attached to an R. Okay? But know that it's in that little ring there, but that's not what we're worried about. What we're worried about is that lone pair. So that lone pair is going to come in. And this is where the E2 dehydration reaction comes into place, at least to some extent. So the lone pair here is attracted to that hydrogen. And it's just your, it's your stereotypical E2 reaction. I hope that's not getting too messy for you, but at the end of the day, what we're left with as a product is an alkene. And this way, because we never had any carbocation formation, we know exactly where it's going to happen, and we know exactly what's going to happen. And H, not necessarily H, I'm sorry. Well, there's a hydrogen attached to pyridine. Pyridine deprotonates twice. Don't worry about that. I'm just going to go ahead and draw OPOCl2. Not important, but I'm going to just go ahead and circle them that these are our products from these reactions. The main thing that's kind of frustrating for a lot of people is understanding that the leaving group here is that's the leaving group you want to make. Why has that become the leaving group and not this? Because we have so much pyridine, and this reaction here is going to happen a lot faster than any carbocation, than any substitution reaction that we could form. So because there's so much pyridine in there, it's going to deprotonate twice in this reaction. And I think I made another video kind of explaining that in more detail. So moving on to the second set of reactions that we have here. I'm going to call it Sockle 2. I trust it's okay if I do that. But anyways, this is also, we're going from a primary or a secondary alcohol to an alkyl chloride. So this is going from an alcohol to an alkyl chloride. So if we're going from an alcohol to alkyl chloride, I feel like I kind of just gave it away. We're doing a SN2 reaction. It's a good reaction to use. So we'll switch colors to blue. So we have ourselves an alcohol. Okay. And we have ourselves sulfur, O, Cl, Cl. You'll see why I drew it that way in a second. And which, I mean, sulfur, it's kind of weird, being weird because it has an octet here, but it's still electron deficient. The lone pair is going to come in, and we're going to have a lone pair attack, and then in the process of that, we're going to release a chlorine. So, next on our list, we have an alcohol here. O positive, H, S, Cl, double bonded to oxygen. So, what does this have? A positive formal charge. Again, you see that and you think, oh man, this is totally going to do, this chlorine here is totally going to just come on in. It's going to do its thing. It's going to immediately do an SN2 reaction because that's the most stable thing to do. But don't forget that we have this, both of these reactions here. We are using, I'll just draw it over here, this molecule in various concentrations. So if we are using this, and then what did I say? The proton transfer reactions are way faster than any other type of reaction, at least for the context of this. Pyridine there. I'm just going to draw it like that. We have pyridine in this, is present there, so it's going to deprotonate that. There, there, back to there. So I'll get a white arrow to show the direction that we're headed in. Hopefully you're used to seeing things going from right to left. So I guess what the end result is this oxygen here that's now quote-unquote more stable than the positively charged, and I'll see if I can get it in red. And this, my friend, this is your leaving group. That's kind of weird. This is your leaving group. This would make a great leaving group too. But because we're having pyridine in the presence here, we're going to get rid of it. This would be actually such a good leaving group that if we had a secondary, well, we may or may not risk the formation of a carbocation. So we have this guy here, and I'm going to go ahead and do it in green. Green, wherever did you go? Okay, so remember this guy here. We lost him. We're not done with him, though. He's going to come back. It's just enough concentration, but there's not as much as we had with the POCL 3. That, remember, this is an SN2 mechanism, that this lone pair here, or a lone pair on the chlorine, is going to come in and do a SN2 reaction mechanism. And I am really running out of room here. I wish I had more space to work with, and that your final products, of this whole reaction that we just took place here, see if I can't draw it in a little bit more detail, is blue. We have ourselves an alkyl chloride and this thing, which we don't really, OSOCl. And I think it makes the distinction that this actually will break apart into SO2. I think that's, yeah. And then another chlorine anion. So I'll just go ahead and circle those in white. So final products, this, which is going to break down into these two things here. We're not really worried about that so much. We're worried about the fact that we've made ourselves an alkyl chloride, which is kind of nice. But it's really frustrating, I guess, understanding the leaving group things. That's something that troubled me when I was looking through that. Okay, getting close to being done somewhat. Now we have PBr3 and the tosylate reactions to work with. And we'll talk about PBr3 really quickly. And again, this is an alcohol reaction, and this reaction exhibits a SN2 reaction mechanism. So go ahead and draw that in blue. We have ourselves an alcohol, hydrogen there, and P phosphorus tribromide, the R with an empty orbital there, and so we just go ahead and draw the, I mean, it's, hopefully this is becoming, you're seeing the pattern here. Oxygen has a lone pair on it. It's going to be attached to that. Our next result is RO hydrogen. Oh, I should have also clarified that PBr doesn't like having that. It's going to leave off there as well. Oh, I'm just going to draw it as PBr2 because I'm kind of running out of room here. And we have a negatively charged bromine. Oxygen has a positive charge. This bromine over here has a negative charge. And that's our solution there. But there's no pyridine. There's no base. No base that's available. So this right here, this little molecule that we have here, this is our leaving group. I'll try not to use so many dots whenever I'm explaining that. This is our leaving group. Okay, and it's a good leaving group to have. It's a positively charged oxygen. Are you kidding me? That's awesome. So, just like any time when you have a good leaving group and a good nucleophile, we're going to undergo an SN2 nucleophile attack. So I'm going to try to see if I can't draw this here. It's going to come in and it's going to do a nucleophile attack. The electrons are going to leave to that positively charged there. That's an SN2 reaction. Don't forget about stereochemistry if there is any. And so the end result is, woohoo, everything went black for a while. Scary. End result is an alkyl bromide and HO. Let's see if it breaks down any further than that. Nope, it doesn't, at least in the context of what my book said. PBr2. So these are our two final products. Again, we didn't have to deal with any carbocation shifts in that whole process. I hope you can recall that. Okay, one last reaction that we're dealing with in alcohol reactions is tosylate. And this is kind of, the advantage of using this is that it can do both. It can be an E2 reaction or it can be an SN2 reaction. Doesn't matter. So how do we know which one it is? Well, it's going to be an E2 reaction if we have, say, you know, a strong base, strong non-nucleophilic base or a bulky base that we're working with. And it's going to be an SN2 reaction, obviously, if we have ourselves a strong nucleophile. Okay, go ahead and write that down. Keep that as a note there. I'm just going to go ahead and kind of do a little bit of a cleanup session here. So tosylate. This is an alcohol reaction. It can be E2 or it can be SN2. And just for purposes of knowing this, because this is something that's frustrated the hell out of me, this is a strong acid. Yeah, that bothered me when I was taking this class. Anyways, moving on to drawing the mechanisms Go ahead and switch to blue here. So I'm just going to go ahead and draw. It doesn't really give a whole lot of depth to what's going on here, but let's just go ahead and let's be as lavish as we like. There's ourselves an alcohol. And I'm just going to abbreviate this as ROTS. And I'll show you what I mean by that later. We'll go ahead and we'll draw out the final structure of it. I mean, I'll show you what I'm talking about here. So that's the overall big picture type stuff of what's going on here. Hopefully we'll have room. If not, we may have to break this down into multiple steps, but I'm okay with that. So we have this reaction here, ROH, and then chlorine, sulfur, being one of those weird things that can exist as an exception to the octet rule. I don't know if you really need to know the structure of this molecule, but it's interesting nonetheless. There's a methyl group attached to that. Whatever. So, oxygen having lone pairs doing the same thing that they've always been doing this entire time, comes in and reacts. And what this gives us is blue. And our next step here, so that was our first step. Try to keep this thing somewhat neat. R, and I'm just going to abbreviate it as OTS just because, well, oh, what the heck, I'll draw it out. But we may run out of room. There's a hydrogen there. Sulfur. Oxygens. I've got to get one of those newer, I guess, things that let you scroll down, or maybe a finer pen. This was not the best tablet I could have drawn on. But anyways, positively charged oxygen, where'd the negative charge go? Well, it's from that chlorine that's just floating around there. From the first reaction here. And so this is where, I mean, it could be E2 or it could be SN2, but either way, what we're working with usually is pyridine. Again, these is a reaction that we have, and I'll go ahead and outline this before the end. I'm just going to draw it as what I always draw it as, NRH. Lone pair here. Again, it's attracted to that positive charge there. Would that make a great leaving group? Yeah, it would, but because we're using pyridine here for reasons that the book does not explain, that's the second step to our reaction here. Kind of running out of room, to be honest with you. And what we have here is RO. S. That pyridine's already deprotonated it, but hopefully this looks familiar to you, that this is this thing right here, this neutral oxygen attached to a, this is our ROTS. And from here we can either do, go ahead and switch to it, we can do, depending on whether we have a nucleophile or a base, we can do an E2 reaction, or we can do an SN2 reaction. It just depends on the nucleophile. But this molecule here, this is the leaving group for this reaction here. So kind of a lot to worry about that. And the thing that makes this, I guess I forgot to mention this, is that this reaction here, this retains the stereochemistry. So that's why this is important, really. That's why it's a pretty useful reaction to use. With that being said, let's just kind of review what we had talked about. So zinc chloride, it's an SN2 reaction. But I guess one of the things that I didn't really list and I really want to stress is superbly important is that this uses pyridine. In a very high concentration, but so does this. The difference between an elimination mechanism and, say, a substitution mechanism between these two is that they're totally dependent on concentration. The difference between any of the reactions that we're going to talk about is that it's totally dependent upon concentration. So these two, and I think I've done an outline for this before, but with this one, this deprotonates twice, and for this reaction here, blue, blue. For this reaction here, it's only going to deprotonate times 1, but both of them involve that pyridine reaction, creating a very goofy looking leaving group. I made a video also explaining that as an outline, but just wanted to kind of talk about it in a little bit more. For the PBr3 reaction, there's no pyridine at all, so we're not worried about that. It's a substitution mechanism. And for tosylate, though, you're also going to see pyridine acting as a base. So again, tosylate, pocyl 3, and I'm going to call it socyl 2. I'm going to start that trend. Those are the reactions that involve pyridine. I'll go ahead and I'm going to write that. So here we see alcohol reactions. With there, there, and there. So alcohol 3. Tosylate. All of these reactions here. Blue. This one, and this one. Every single one of these things works with pyridine.